My name's Abdulhai Naqvi. I'm a software engineer with Wind River Systems. They make embedded operating systems. And I've been mentored by Dr. Waqas Birni at CERTS for a project in handwritten digit recognition. So this falls under the domain of image recognition. And I've implemented a machine learning algorithm called KNN to recognize digits, handwritten digits from 0 to 9. So a little bit of background on what the problem is. Um, Image recognition, it's a vast problem, and there's a lot of cutting edge research. KNN is a relatively simple machine learning algorithm. It's called a non-parametric supervised learning classifier. And I was able to implement this in Python, and I will give you some of the details and some of the analysis. So to start with, what does non-parametric mean? It means that there are no parameters that come from the data that the algorithm takes. For example, nothing related to the data that needs to be tuned in the algorithm. That's what non-parametric means, meaning the algorithm doesn't really care about what type of data it's given. And supervised means that training and testing data are separate. So what is training? We take some data, we have a data set, and we split it into two called training and testing. And we train our classifier on the training data. And then testing data is what we use to test the accuracy of the classifier. And that's what supervised learning means. And this algorithm is relatively simple. It is ideal for low power electronics, real-time scenarios. It has a few Achilles heels, such as not being good when there is a lot of training data. And I will explain to you why in a second. But it has been used successfully for disease recognition as well, to tell whether somebody is sick with, for example, a particular type of cancer, or to detect heart disease in patients and such. So this is a relatively mild example of what it can do. The data set that I'm using is called MNIST, MNIST, and it is a data set collected from US Census Bureaus and high school students by NIST. And you can see that each of the images is, they look, if you see on the poster in figure 3, they are 28 by 28 pixel images of the digits 1 to 9. And I believe it might be 0 to 9 or 1 to, I think it's 1 to 9. And I will tell you now exactly what I did. I took the data set, and there are 60,000 images that are for training, and then 10,000 images for testing. And I'll explain to you exactly what KNN does. KNN takes an image, and which we will call one of the testing images, and it calculates the distance between that image and all of the training images. And the K in KNN, it stands for K nearest neighbors. The K means let's say I'm doing 3NN. So I'll take the 3 nearest neighbors of that particular test image, and I'll see what the label is. So let's say the test image I'm looking at, I don't know if it's a 1 or a 2 or a 3, and the closest labels are 2, 3, and 3. So I will take a vote between the 3, and I will say that 3 is my mystery image. That's the label for it. So we take each of those images, we flatten them into a vector. So they're 28 by 28 pixels. So it's a single dimensional vector of 784 pixels, or 784 features, if you may. And we use Euclidean distance and cosine distance and Manhattan distance. Euclidean distance turns out to be good enough for application. And basically do a lot of distance calculations, store those distances so we can reuse them again and again. And that's the gist of what KNN does. And I will tell you, I have some code that I was not able to fit on it, but you can find SciPy that implements KNN. I'll tell you some of the libraries that I used. I use Pandas. It is a data processing library from Python. It's really useful for working with data records. And NumPy for their built-in arrays, C-like arrays, also very fast. And I used Matplotlib to make these visualizations that you'll see on the poster. And I also use Dask. This is a library that is for distributing workload to make computations more parallel. And I was able to use the different CPUs in my processor in my home computer to make the calculations a little bit faster. So basically, that's the methodology here. And now let's talk about what the results are. If you notice figure one, it tells you what the accuracy for different training data sizes is. And as you can assume, accuracy improves with training data increases. But you'll really notice that the improvements are somewhat meager after about 1,000 or 2,000 training data. So this kind of leads you to the one of the results, and I'm being preemptive about it, is that you don't really like in a real life scenario. For example, if you're putting KNN in a car and you're checking whether you're seeing a stop sign or not, or what type of sign you're seeing, you don't really need to have a vast data set for training. If it's representative enough, of course, that carries a lot of, it's highly context dependent on what's representative enough. But in this case, 1,000 images or 2,000 images would suffice to get up to 85% accuracy. But as you can see, we get around 96% accuracy with 10,000 testing images, with 10,000 training images. And here, K is set to 3, or I believe it's set to 5 actually. If you notice figure 2, this shows you K for different training data sizes. There's not much difference if you vary K. There is another way of finding what the best K is. For example, if you're working with something else, a different value of K might be the ideal value. And in our case, it turned out to be 5. If you notice figure 4, this uses cross-validation. So some of the figure labels and the actual image headings might be wrong, but the figure 4 heading on the poster is correct. Accuracy would vary in K using cross-validation. So using cross-validation, where you split the data set into 3 different pieces, where you have training, cross-validation, and testing data, you can see that the value of K that minimizes, again, sorry about that, it's mislabeled accuracy, that minimizes error is the value K equals to 5. And this is the value that is chosen basically at the top. Again, apologies, it says K set to 3, K set to 5 in figure 1 to get 96% accuracy. And you can see it on figure 2 as well. Figure 6 is basically one of the images, ones. So what we get from KNN is certain images are, you have an error that you can calculate. And basically, these are all images of ones, or sorry, all images of 6 that are classifier set. These are 6 at the top in figure 3. And these are the best, these are the worst on the top that are labeled as 6, meaning that when you actually compute the errors, these are the furthest from actual 6s. Meaning, if you calculate the error, these are the highest error in all among all images that are classified as 6. And at the bottom in figure 3, these are the images that have the lowest error, and they're still classified as a 6. And you can see the lowest error, they all look like 6. And the ones with the highest error, most of them do not look like a 6. You'll find 1 or 2, but they mostly look like 1s or 7s or something else. The classifier is not that far off, and a human would also have trouble with some of these images. But of course, there's room for improvement. And I would say in future direction, further improvements can be put into this. One could try different distances like Minkowski distance, Hamming distance. I would say that KNN, in conclusion, it's a good classifier if you want ease of implementation, especially if you're working with what is called edge computing these days, small computers, for example, like a TI computer or something where you're not necessarily don't have all potential libraries like Python and whatnot. You could implement this in C. You can implement this easily in most languages. And basically, as you can tell, the training and testing are really the same thing. When you do a test, you run against all training data. So as long as you can store the training data in memory somewhere, you can run KNN, and it's usually a good choice or a classifier. And another good thing about KNN is that it works well with nonlinear data, especially, and you don't, it's non-parametric. You don't have to really tune any parameters except K, which is called a hyperparameter. It has nothing to do with data itself, K. And I would say it makes it a good classifier, especially image recognition, but also disease recognition and a lot of other areas, basically. And I would really like to thank Dr. Waqas Bernie and CERTS, and thank you, everybody.